that you may not know what they're talking about. So it's fairly basic information. So it's astronomical names, or the naming of objects, and catalogues that these objects are contained in. So it's useful to be familiar with this stuff. So a catalogue is a pretty simple thing. It's really just a list of anything really, and it'll have information about the items in the list. So for astronomical objects, for us on Earth, the most important thing is to know where the object is in the sky. And so what we require to do that is some kind of system of coordinates. So tonight I'm mainly going to be talking about the official IAU names, because each culture has its own names for astronomical objects, stars, asterisms. So these are the ones that I'm going to be talking about, the ones that are defined by the International Astronomical Union. And they're mostly based on the Western system of constellations, which I'll explain. Okay, so the first thing is coordinates. So how do coordinates work? You're probably familiar, if you're on the Earth, we have a system of coordinates on the Earth, and you can find out where you are from your phone. If you've got a GPS receiver on your phone, it'll tell you your latitude and longitude, and it's quite accurate to within a metre or two sometimes. Obviously good enough for navigating the car around the city. So this is a technology that's pretty amazing, especially if you were a mariner back a few hundred years ago, to be able to know to that kind of accuracy where you were. But on the Earth, you'll be familiar with latitude, and you have circles of latitude that are called parallels. Like you might have the 30th parallel. The 90th parallel is actually the equator, and the 0 parallel is just actually a point at either the North Pole or the South Pole. And in between, you just have an angle that tells you how far you are north or south of the equator. Those are defined actually by the rotation of the Earth. So the Earth, if you look at the stars, you'll find they rotate about 2 points in the sky, one the North Pole, one the South Pole. And that system is just projected directly onto the sky. But on the sky, instead of latitude, it's called declination. So, whoops, didn't mean to press that, sorry about that. Go back. So the declination is just how far the object is north or south of the celestial equator. So you can just think of it as latitude projected onto the sky. Longitude you'll have heard of on the Earth. Because the Earth is rotating, or if you look at it from the point of view from what we see, it appears the sky is rotating. We need some kind of a reference point. On the Earth, you can choose some arbitrary place and say this is the 0 point for going east or west. And at the moment, that was defined by the Greenwich Observatory, because back in the day they had the best transit telescope there, so they could get accurate astronomical measurements. If you have a look on, I don't know, there's some people go to London and go to Greenwich and they get out their phone and they're expecting to see 0 latitude and longitude on the marker on the ground. But if you do that, you'll find it isn't. In fact, the GPS is about 100 metres away from the actual marker point. And the reason is that GPS uses a kind of a model of the Earth's surface that's an equipotential based on the centre of the Earth. Whereas when the astronomers at Greenwich did it, they used a bath of mercury to figure out the local horizon. But the problem is the gravity from place to place isn't truly directly at the centre of the Earth because of local differences in density. It's kind of a weird thing, but that causes the GPS prime meridian to be slightly different to the one That was defined as the Greenwich meridian. Doesn't matter anyway, but just an interesting little factoid. So what we do for celestial coordinates, we haven't got a fixed place on the Earth that we can use. So what is done, or what has been done, is to use the celestial equator and the ecliptic. The ecliptic is the path of the sun across the sky during the year, called the ecliptic because eclipses of the sun and moon can only happen when the moon is crossing the ecliptic. The sun is always on the ecliptic, but at times a full moon on the ecliptic or a new moon on the ecliptic, you can either get a lunar eclipse or solar eclipse. So in fact there's one coming up, is it the 9th of November? One coming up in November anyway, a lunar eclipse. So if we get a clear night, that'll be quite good. I think it's maximum at midnight. Right, so midnight on the 8th of November, something to look out to observe. So what happens is at the moment we're in spring in the southern hemisphere, so the sun has just moved to the south side of the celestial equator. So the origin point is actually taken from when the sun moves into the northern hemisphere spring, so the March equinox. And though that crossing point for the March equinox defines the equivalent of the Greenwich meridian, but for things in the sky. And it's got some funny names, like it's called the first point of Aries, you may have come across. And the weird thing is it isn't in Aries anymore, it was 2,000 years ago. But unfortunately, because the Earth's north and south pole actually wobble around over, I think it's 25,000 year period, the first point of Aries actually moves over time along the ecliptic. So did I say what that's called? No, I didn't. That equivalent to longitude in astronomical terms is called right ascension, and the 0 point is at the vernal equinox crossing, and it's measured not in degrees like we do for north and south, it's measured in time. So we have 24 hours. Okay. Another thing you may come across is what's called the hour angle. And what the hour angle is, it tells you, if you see a program you're running to show you the sky, and it will tell you the hour angle of an object, this tells you how far away the object is from crossing the meridian, which is the line directly above your head. So the convention is that if it's to the west of the meridian, the hour angle increases. So if the hour angle is 0, that means the object is going to be straight overhead or along that north-south line, crossing that line at the time. And then 3 hours later, it'll be over here somewhere, and so on. Some of the programs will show negative hour angles for things that are on the east, and others will just do it as like a 24-hour clock where you, these ones will be something like 1900 or 2000 hours or whatever. But some report it as plus and minus, going to plus 12 and minus 12 hours. So just be aware of that if you get confused. I think stellarium does it as a plus 12 to minus 12 hours for the hour angle. But it's useful if you're observing, because if you see so it says the hour angle is -5, then you know it's going to be quite a long time before that star or planet is right up high in the sky. So it's a useful little bit of information. Okay, that's enough of the basics on coordinates. There's actually a lot of other subtleties to do with it because of, as I said, the Earth wobbling around on its axis. Actually, I'll just, before I leave that topic, I'll just show you, oh, no, I won't actually, I'll come back to it later, there's a better point to bring it in. Okay, so we're looking at catalogues of objects. This guy here was a ethnic Greek guy. He lived in the time when Greece was under Roman control. And he did the first known, there may have been others that we don't know about, but quite comprehensive catalogue of stars. He also was the person who is believed to have discovered the precession of the equinox, as I was talking about, with the Earth wobbling around on its axis. Now, he had a star catalogue of about 1,000 stars. So that's quite a lot to work on, to work out their positions in the sky. So that was pretty unique for that time. So this is, apart from that catalogue he was famous for, he also discovered this axial precession, as it's called, or the precession of the equinoxes. So the Earth wobbles around, as you can see in the diagram there, every 26,000 years. So if, at the moment, if you're in the northern hemisphere, you have Polaris, the pole star, in 13,000 years. The pole will be pointing quite a long way from Polaris, because it'll be pointing over here. So if Polaris is up this way, 13,000 years, it'll be no longer anywhere near the Earth's pole. But in about 7,000 years, the good news is we get a pole star in the southern hemisphere, Delta Velorum, so we'll have the advantage then. Yeah, about 7,000 years, I think Delta Velorum, so something to look forward to. Right. Other thing is to do, apart from star catalogues, the other thing we've got to worry about is constellations. And historically, these were just nice patterns of stars that people recognise and associated with something of mythological origin. For example, this one is showing the hunter Orion holding his club, and you can see the belt stars, and I think that's Betelgeuse. It's upside down for us because we're in the southern hemisphere. We've got to turn everything over, and that will be Rigel down by his ankle there. And the three belt stars, Alnitak, Alnilam, and Mintaka. So this particular drawing is actually from a plate made by Johann Bayer, and he decided they need to have like a map of the sky. And so he did these really engraved plates. It was quite a big job with all of these figures on them. And this is the plate for Orion. He had 48 constellations, but they were mostly northern hemisphere ones. And the names of these and the figures were basically came from Greek and Babylonian ideas about the heavens and the zodiac and so on. But they're quite artistic, some of the figures. And I don't know where the originals are, but I imagine they'd be quite valuable. I believe they still exist. Yeah.
The lines of declination and the sidewall tiles, so I see that's already got lines on it.
Yeah, they had quite decent instruments. This is from about the year 1600 or thereabouts. Remember, Tycho Brahe already had set up his observatory, and they had huge quadrants that could measure angles down to 1 arc minute. So they already had reasonably good measurements. This is before the invention of the telescope, though. So the limiting thing was actually the resolution of the human eye, and that's around about 1 arc minute. So that was the best they could ever do, no matter how good the instruments were. He did his 48 northern constellations, but this one is interesting because by that time they'd heard reports from mainly Dutch navigators that had come to the southern hemisphere and reported that there's a whole lot of stars down there you can't see from the northern hemisphere. So he did this one plate to cover the southern hemisphere, and you can see you've got, the Peacock, that one is Indus, and you've got Grass the Crane, Tucana, Phoenix, and there's a water snake called Hydrus, Dorado, and Volans, Chameleon, and Apis, and there's also Triangulum. The weird thing is, you've got Musker the fly there shown. Now, I don't know why on this plate he's written, it's got Crux and Bitgrave there, but it doesn't show any stars. And I'm not sure whether there was a separate plate for Crux, I don't really know. And it only shows Alpha Centauri and none of the other stars of Centaurus. Centaurus definitely does have a plate, so that might be why. Most of these names are generally still in use, but one thing you notice, it shows stars and it shows pictures, but there's no clear delineation between where one constellation starts and stops. So that's a bit of a problem if you want to catalogue things accurately. So they came up with a system of the IAU, and the ancient 48 constellations, they tried to keep with those as much as possible. They added a bunch of new ones for the southern hemisphere, and the southern hemisphere was mostly, I think it mentions here, some Dutch navigators and Louis de la Caille, who was a priest, and I believe he did observe possibly from Cape Town, I recall. And so they wanted to have clear boundaries of where stars were, because if you look up a catalogue and it says this star is in Orion, was it really, or is it actually in the adjacent constellation? So you needed some kind of system to figure out where to place the stars. So, and I'll now flip to a stellarium, because what it says here is that the boundary is defined by line segments, constant right ascension and constant declination. So we can look at that if I bring up a star mapping program. So you can see the red lines are actually the constellation boundaries. And you see some of them are not at all simple. And they've had to do that because they just didn't divide the sky up into 88 equal chunks. They tried to keep with the traditional constellation names. So the lines had to be drawn around the various objects, like we mentioned Chameleon before. And see that curved line is a line of constant declination, and this is a line of right ascension, but the Chameleon one is pretty straightforward. It's just got 4 lines. Some of them are obviously a lot more complicated, like Dorado. So a bit messy, but they didn't want to throw out the traditional constellation names. The curious thing about it is that I mentioned precession before. So I'm just going to show you something in this program. We can actually well, first of all, I'll turn on the equatorial grid. So that's showing you the actual current lines of declination and right ascension. So the declination lines are these ones, which are showing you degrees north and south of the pole, or the equator, depending on which way you want to look at it. And these are the lines of constant right ascension. So it kind of looks okay there, although you might notice that the lines may not be exactly parallel. So let's go forward in time. Whoops, not that one, on the clock. So let's go to, say, the year 12,000. And look what's happened now. The constellation lines are massively skewed, and that's because of the effect of precession. So what they had to cater for this, what they did is they defined not the lines of right ascension and declination as it is at whatever date you were at, but at a specific date. And it's something weird like 1875 it's based on. But the scheme was made up in the 1920s. So to stop that drifting from happening, they don't use the coordinates of the current date, they use the coordinates back when they made up the system. Right, let's flip back if we can. So that's much as I wanted to say. Oh yeah, it tells you here that the term epoch is used when they're talking about the coordinates as they were at a specific date. The current one that's used for most catalogues is what's called J2000, is based on the Julian year 2000. B stands for Besselian year, which had a different start date to the Julian year, just to confuse things further. Unless you're really doing detailed programming of a program like Stellarium, you don't really have to worry about that. So here's an example of a modern constellation. It's Orion again. And as you see, to keep the tradition, they have to have quite a complicated boundary with a lot of little kinks in it to get the stars that you were traditionally known to belong to that constellation within the boundary. So these are the 88 constellations. They all have a 3-letter abbreviation. Like we were talking about Orion before, you can see that the abbreviation is ORI, and then it gives the full name. So if you see something like Alpha Ori, then you know that's Alpha Orionis, and so on. Okay, so star catalogues, there's a lot of these used for different purposes, and they will have different information. But some of the common ones is the proper name of the star, and a proper name is something like Sirius or Rigel or anything like that, where it's not just like a catalogue number and letters or anything like that. So they're the generally well-known names, and they are the ones that come from the Western system of star naming, which basically goes back to, as I said, ancient Greece and Egypt. And there's Arabic names in there as well that got put in during the Middle Ages that have been retained. And you have like there'll be some kind of a ID depending on the catalogue. It's usually just a number. So you might see something like HD 29436. It just means that it's that star number on the HD catalogue. And I'll talk a bit more about some of the more common catalogues that you'll come across. Obviously, you have the position of the star, and you can have things like brightness. Parallax, what that really is telling you, the information that tells you is how far away the star is. But astronomers measure that, they can measure it in light years. It's a common measurement for how far away things are. But it can also be measured as a parallax angle. So parallax angles are really small, like the nearest star, Proxima Centauri's parallax is much less than 1 second of arc. We've got the spectral type, and they can have all sorts of other information depending on what the catalogue is used for. You can have proper motion, because although we see the stars seem to be in the same position year after year, if you examine them really closely, they are actually moving relative to each other. And that's especially the stars that are closer to us, they appear to move more than the ones that are far away, just like if you see somebody walking close to you, they'll move quickly. If they're a long way away, they appear to move slowly. With stars, it's just the same. The motion is very small, but with the telescope, it's quite easy to detect the proper motion. There's also radial motion, so is the star moving away or towards us? So Catalogue might tell you that information as well, and lots of other stuff. Just a bit more on proper names, mostly either Arabic or Latin derived. There's a couple of strange ones that have been thrown in there, and recently there's been some new ones. As you see, the IAU back in 2016 set up a working group, and there are now 227 official IAU star names. And I don't know why, but they named Alpha Centauri, that would always refer to it as, it's now called Rigel Kentaurus. Apparently because navigators referred to it like that. And there's a few other new ones that they came up with. Weirdly, Proxima Centauri is the official name of that star, even though we can't see it. You need a telescope to see it. Generally, all the other stars that have names you can just see with the naked eye. So gets a special consideration because it's our nearest neighbour. And it says there, for example, the visual magnitude of the star Sirius is the brightest star in the night sky. And Proxima Centauri is magnitude 11, which is way below what you can see with the naked eye. So some other designations for stars is the Bayer designation. Those engravings I was talking about of the constellation, he's the same guy, Johann Bayer. He came up with the idea of ordering the stars by brightness along with the Greek alphabet. So generally alpha was the brightest star in the constellation, beta the second brightest. So that's where that comes from. There's a few funny exceptions in terms of brightness where they're a bit out of order. And there's a Flamsteed designation, which is a kind of you'll possibly see sometimes. And it's within a constellation again, but they have a number in front of the constellation, and they're in right ascension order, going from east to west. So one Eridani in this system would be the easternmost star in Eridanus, and so on. I don't see that so often these days, but you do occasionally come across it. Already talked about position, so just quickly mention we have the declination, right ascension, and as it says in the note at the bottom there, due to precession, we have to specify what epoch these coordinates apply to. When you run a program like Stellarium or Sky Safari, any of those, the program knows how to convert from the catalogue coordinates to the current coordinates, because it's a simple calculation. Just basically process the coordinates to the current date. Okay, star brightness. This is system is really based on the guy Hipparchus as well. What he did in his catalogue, he had a ranking from the stars, first rank to sixth rank, and he called it first magnitude, second magnitude. First magnitude were the brightest stars in the sky that you could see, and the sixth magnitude were the faintest. He didn't know that there's seventh magnitude and eighth magnitude stars because he couldn't see anything fainter than that. So as far as they were concerned, magnitude 6 was the faintest stars. But the problem is that with things like the Hubble Space Telescope or the Webb Telescope, you can go to magnitude 32 and beyond. And of course there's things that are brighter than the brightest stars. So down here we have the sun. So the modern way to do it is to extend that old Hipparchus system to objects of any apparent brightness. So obviously the brightest thing we've ever seen is the sun, and the faintest thing only show up on long exposure photography on space telescopes. But they also defined exactly a quantitative method of doing this. And it works out that to get the scale to work, the difference between a first magnitude and the sixth magnitude stars is approximately 100 times difference in brightness. So a difference of 5 magnitudes is a 100-fold difference, and that applies to the modern scale. Sorry, I keep hitting the wrong button here. So a difference of 1 magnitude is the 5th root of 100, if you know your mathematics, 2.5 roughly. So 1 magnitude is roughly 2.5 times brighter. So a second magnitude star is 2.5 times fainter than a first magnitude star under this system. They used to use Polaris as sort of like the definition of magnitude 2, but then it was realised that Polaris is a variable star, so that wasn't going to work. Then they decided to change to Vega, which came out at magnitude 0, but it also has slightly variable, so now they just use an instrument measured flux of the star to calibrate the system. You know, that kind of brightness we've been talking about there is apparent magnitude. That means how bright it looks to us here on Earth, but it doesn't tell you how bright the object really is. Like I talked about, the sun seems incredibly bright, but it's a lot fainter than, say, Rigel in real terms. It appears brighter because it's much, much closer. If we had Rigel sort of sitting right next to the sun in the sky, then it would be incredibly brighter than the sun, thousands of times brighter. So we have the concept of absolute magnitude. So the absolute magnitude that you'll see in a catalogue or given an information about a star tells you how bright the star would appear to be if it was at a fixed distance of 10 parsecs, which is 32.6 light years. Parsec is just another way of measuring distance related to parallax that we talked about earlier. So when you see something of if you had an absolute magnitude of minus 26, that would be an incredibly bright object, because it would be as bright as the sun at the distance of 32.6 light years. Spectral type is another thing that you can find in the catalogue. And they have these funny letters, O, B, A, F, E, G, K, M. And this goes back to, I think, an astronomer called Annie Cannon came up with this system. And she worked for the Harvard Observatory when they were preparing the Henry Draper catalogue. And it was the first time spectra had been used to put in their catalogue, so they had spectral information about stars, but they didn't really understand spectra, and they started off with A, B, C, D, and then it didn't work, and they ended up with this strange looking system. And it turns out that if they're in the letters are in this order, then it's basically in temperature order. So the spectral class O are the hottest stars, and M is the coolest. And they can be divided up into subcategories, so you go O2 through to O9 if you divide it up that finely. And of course our own star, the sun, is a type G, and if you go to the subcategory it's G2. And then you have another letter, the letter V means that it's a main sequence star. We won't talk about what that is tonight, but I'm sure Chris talks about that in Introduction to Astronomy and other people he has on those talks. That letter, it is listed in the table below, just in case you're want to see the sort of things like a 1A is a luminous supergiant, V main sequence, and you've got bright giants, subgiants, and so on, down to white dwarfs. G2V is us, so we're luminosity class V, main sequence dwarf. So you probably often heard the sun referred to as a yellow dwarf. So yeah, most main sequence stars, except for the really extreme O class ones, are considered to be dwarfs. Like you've heard of red giants and blue giants. So if you study things about the Hertzsprung-Russell diagram, it sort of explains this in more detail as to what's going on with that. Right, some of the common ones you might come across. The Yale Bright Star Catalogue, and this is quite a good one for just for visual astronomy, because it goes down to magnitude 6.5. So if you see a star that says HR followed by a number, then it comes out of this catalogue. One that used to be around quite a lot, but I haven't seen for a while, is the Bonadurch-Musterung. So this is obviously the star was done with a telescope. This catalogue was compiled using telescopes. It's astrometric, in other words, it's telling you the position of the star to fairly high accuracy, and it goes down to 10th magnitude. And it's, as it says, they divide the sky into zones, and then a number within the zone of declination. So every zone of declination is sort of like a separate catalogue, if you like, in this one. The Henry Draper one I talked about. The reason it's Harvard Observatory, the reason it was named after Henry Draper, because his widow actually paid for this catalogue. Henry Draper was an amateur astronomer. I think he was a medical doctor. He was very well off, and he was he was an amateur astronomer who was a pioneer in astrophotography. And I think he was the first person to ever photograph the Orion Nebula. But he died, and his widow decided she would have his name up in lights, so she financed Harvard University to produce this catalogue, and that's where the name comes from. Interestingly, there are some famous women who were involved in this. Apart from Annie Cannon, there was Henrietta Leavitt, who discovered the Cepheid variable distance relationship. When she was studying the Magellanic Clouds, she found there were Cepheid variables in those clouds. And because the clouds, you realise all the stars in each cloud are about the same distance, she noticed that the variability was related to the observed brightness. So this team did some really foundational work in modern astronomy. SAO is the Smithsonian Astrophysical Observatory. It's another astrometric catalogue, fairly out of date now. Hipparchus catalogue. It's an acronym rather. High precision parallax collecting satellite, but it was also trying to make a play on Hipparchus, the Greek astronomer. So up until recent times, that was the most accurate catalogue in terms of position, because it was done from a space satellite. So you haven't got a problem with the atmosphere distorting the observations. And then there's the Tycho US Naval Observatory catalogue. Position information based on Hipparchus, but they had quite a lot more stars in there that were catalogued from ground observations, so about 2.5 million stars. And then there's some US Naval Observatory done all these ones. This USNOB, 1,000,000,000 stars done from photographic plates, and then the UCAC4, which is still in use, done from CCD images. This catalogue is so big, it's not in one big file. You have to download it in parts, covering the section of the sky that you're interested in. And pretty much these are mostly going to be obsoleted by the Gaia catalogue, which I think we've already had data released to. This is from another satellite, similar to the Hipparchus satellite, but launched by the European Space Agency, and it's much more accurate astrometry. Like, it can go down to something like 10 microarc seconds per position, which is pretty incredible. It also does multicolour stuff, so it can figure out star temperatures, so it can measure proper motion to high accuracy and things like that. So it's not finalised yet, because I think the satellite has still got a couple of years more observations to go. And I think the revision 3 of the catalogue is coming out at the end of this year or early next year. Each time they have another data release, the data becomes more and more accurate, because they're measuring the same stars over and over again. There's something like 1.5 billion stars. So the full catalogue will take up a lot of space on your hard disk. So now you come to a problem. You see a star name and you think, oh, what the heck is that? And then helpfully this down the bottom there, this is the University of Strasbourg in France. They have this site called Simbad. If you just Google Simbad star catalogue or something like that, it's an online interface. And if you've got a catalogue name of a star, for example, you saw something like HR 1457, you just type that in, and then it'll give you a screen like this of all the, whoops, not like that, all of the associated identifiers. So, for example, you can see Alpha Tauri, Aldebaran is the proper name of the star there. US Naval Observatory catalogue, Tycho catalogue. So Bonadus Musterung in the +16 zone. So yeah, if you're really eager to know what a star actually is and you don't recognise that catalogue name, it's reported in the press or something that they've discovered something interesting about such and such a star, plug it in here and then it might come up with something that you recognise if you're lucky. Okay, there's also variable stars have their own catalogue and nomenclature. So they will be named after the constellation they're in, but instead of a Greek letter, they use a Roman alphabet capital letter. And they went through the letter R through the letter Z, don't ask me why. But trouble is, when they discover more variable stars in a constellation, which you can guarantee there will be, they ran out of letters, so they go to RR to RZ, SS through SZ, to ZZ, so you get a lot more stars. And then they started using AA to AZ and so on. And then all the combinations exhausted, they go to numbers. So you sometimes see a V followed by a number. So that's within a particular constellation. So probably the best catalogue is the general catalogue of variable stars. A lot of amateurs observe variable stars. You get finder charts from the American Association of Variable Star Observers. You can do it visually. They give you a field to look at, and you just visually, looking through your telescope, try to bracket the star of interest between two adjacent stars. You might say, oh, it's sort of part way in brightness between these two. And we know this one is such and such a brightness, the AAVSO will tell you. and you make an estimate of it to like exactly halfway between, you can come up with a magnitude estimate. And people can get down to, if they're really good at it, about 1/10 of a magnitude, which isn't bad for visual estimation. But it's not really necessary these days because most people have access to digital cameras, and software can read the magnitude directly off the, by comparison to stars on the same image, they can measure the magnitude. A lot of astrophysicists are interested in this variable star stuff because following the light curve of stars can tell all sorts of information about the system you're looking at. And then some of the variables are not just simple sort of sinusoidal things. You get all sorts of irregular things happening, and they try to come up with theories to explain what's going on. We haven't got too much to say about the remaining catalogues. It's mainly what we call deep sky objects. These are things that don't belong to the solar system, but they're considered deep sky, and this is things like clusters of stars, nebula and galaxies. And you see down the bottom, if you have a star charting program, these symbols are quite standard, not the colours, but if you see an ellipse like that on a tilt, it indicates a galaxy. A circle dotted line is an open star cluster. Circle with a cross in it is a globular cluster, another kind of star cluster. If you see this thing that looks like a crosshairs on the outside of a circle, is a planetary nebula. Planetary nebulas are actually dying stars that are similar stars to the sun that have reached the end of their life. And in the last burst, they throw off their outer atmosphere, gradually expands into space, sometimes forming really complex and interesting looking patterns. If you see pictures of these on the web, internet, or if you're into astrophotography, you can image these things. Some of them are quite interesting. Bright nebula is like the Orion Nebula, for example, is a bright nebula. And they'll show just a dot for a star and an open, symbol with a white inside for a variable star. This is really for printed charts, but most of the planetarium software follows a similar scheme. So when you're looking at your program, Stellarium, you can see the symbol, you say, oh yeah, that's a galaxy, and then you can zoom in on it. So a really common catalogue for these things that amateurs will come across is called the Messier catalogue. So this is due to Charles Messier and Pierre Machin, who lived in France. They were actually not interested in these objects. They were actually comet hunters. But they would come across these things and think, oh, is that a comet? And they'd be disappointed. No, it's actually a useless galaxy. They made up this catalogue so that comet hunters wouldn't be confused. Some of them don't make a lot of sense, like the Pleiades or Matariki cluster M45. It's pretty obvious to anyone that it's not a comet. You can see the stars with your own eye. So there's a few things like that. I'm not really sure why they're in there. I guess it is a star cluster. The total catalogue is 110 objects, but it's very much northern hemisphere centric. So we have objects in the southern hemisphere that we look at, like Omega Centauri, 47 Tucanae globular clusters, the jewel box cluster. They won't be in the Messier catalogue because they're too far south. And most Messier objects are fairly easy to observe. They did have the advantage there was no electric lighting back in those days, so even in Paris it was fairly easy to see the stars when the moon was out of the sky. So generally these are pretty easy objects to see in a small telescope, but you often will find you need a dark sky, so the centre of Auckland isn't a great place for observing these things. So Patrick Moore decided that Messier had missed a lot of objects and he had nothing much in the southern hemisphere. So he came up with this catalogue called the Caldwell catalogue, which was the same sort of idea, that it would have objects that would be of a lot of interest to amateur astronomers, but it would cover the southern hemisphere as well as some objects that were missed from the northern hemisphere that Messier missed. So, for example, Caldwell 106 there, 47 Tokene, also called NGC 104. I'll talk about NGC when we'll get to that on a later slide. There's also one called the Bennett catalogue. Jack Bennett in South Africa came up with a similar idea to the Caldwell, but it's purely southern hemisphere only. So everything is south of the equator in this Bennett catalogue. One that we see a lot is an all-sky catalogue of deep sky objects. And this is the new general catalogue of nebula and clusters of stars, and it was new back in 1888. So this was compiled by a lot of work by Carolyn John and William Herschel and others. So this was all done with visual stuff, but quite large telescopes in both hemispheres. I think Herschel's largest telescope had an 18-inch mirror, something like that. So pretty large for the time. And then Dreyer came along and they were starting to discover a lot of other objects that couldn't be seen visually but were coming up on photography in the early days. But the problem is the NGC numbers are in right ascension order. And you can see there's a bit of a problem there, because if you discover a new object between two objects you already knew about, do you say NGC 104.5 or something like that? So they decided they weren't going to do that. So they added index catalogues 1 and 2. So you'll see objects called NGC something, but also IC something. So the IC or the index catalogue is these extra objects, because you can never go back and adjust the NGC catalogue because of the fact that it's ordered by right ascension. So you could, if there was something between the highest numbered one and NGC 1, you could extend it that way. But okay, specifically a galactic catalogue, you might come across as the term PGC, as a principal galaxies catalogue. This has got a lot more galaxies than the new general catalogue. Over 70,000 objects, and some of them have different information, like some will have morphological description, like is it a spiral or an elliptical, that kind of thing. Others are not really sure what they are. They're just a very faint blob that's hard to make out what it is. And they'll say whether it's got an axis, a directional axis, or tilt, if you like. And most of them, they've listed apparent magnitudes, radial velocities, and things like that. So that's fairly commonly used still. And there are other catalogues of galaxies that are really only used by professionals. Other catalogues of interest, we're nearly at the end. The Malott catalogue, and you'll sometimes see this. This is a catalogue of star clusters. Some of them are duplicates of things catalogued in the new general catalogue. Yeah, it's not really commonly used, but I do come across it in things like they'll say, oh, this is a photograph of Malott something or other. And then you've got Barnard's catalogue of dark nebulae. So these are things like, I don't know, if you look down the Milky Way, on a really dark night, you can see that there's dark bands running through it. and these are actually not areas where there are no stars, but there's actually obscuring dust and gas blocking the stars behind, and they're referred to as dark nebula. And so Barnard catalogued 370 of them. Most of them are only readily visible in photographs, but some of them you can see naked eye. For some unknown reason, he missed the Coal Sack Nebula, which in the Southern Cross, which is really easy to see with the naked eye from the dark sky side. Right, we've just got the solar system to go. We're a little bit over time, so I'll go quickly through this. Particularly interested in comets and asteroids. How are they named? So they had things like the Great Comet of some year, or Halley's Comet, that kind of thing. Generally, this type of comet, the Great Comet, would appear, and then they might have been able to calculate its orbit by this time. Some of them had orbit maybe 100,000 years, so effectively they don't really know whether it's coming back or not, because they don't know how accurate the orbital calculation was back in those days. But some of them were recognised as periodic comets, where they will be able to predict a return of the comet, and probably Halley's Comet is the most famous one and the first such comet. So it's called 1P Halley. So the second such comet would be called 2P, named after somebody else. This is a situation where you can have an astronomical object named after yourself. So as the discoverer of a comet, you get the comet named after you, if it's a periodic comet. Unfortunately, there are very few pickings available now with all of the automated sky surveys going on. So there's a general naming scheme. If it's not a periodic one, it's just called C followed by the year it was discovered. And two letters, the letter H is the half month. So for example, it says here that if it was discovered in the second half of the month of February, it's the letter D. And then the number goes up for each number of the half month. So one that was really famous a few years ago was really bright, and you could see it during twilight in New Zealand. It was so bright, and Australia as well. Comet 2006 P1 McNaught. You know, the letter P is again tells you which month or half month it was discovered in by an Australian astronomer, amateur astronomer. And 1 is the first comet of that part of the month. If you look online for this one, there was a lot of photographs taken from Australia and New Zealand. Asteroids, a little bit similar. You have, they get a provisional year and again a half month and a letter. And then once the orbit of the asteroid is confirmed, which requires follow-up observations, then it gets an official number. And for example, the first asteroid is 1 Ceres, although that's now been reclassified as a dwarf planet rather than as an asteroid. So that's kind of a special case. If you're into the Pluto controversy, you'll know all about that. Some interesting ones here. 19620 Auckland, 23966 Maungakea, 23990 Springsteen. Those three were all discovered right here at the observatory by a guy called Ian Griffin, who's now the CEO of the Otago Museum, I think it is. Is he still there? Yeah. Yeah. He was the, he used to run the Stardome here back in the day. But the final one there, 386622 New Zealand, was discovered by Society member Jenny McCormick out at her Farm Cove Observatory, at her home observatory. She decided, the discoverer gets to suggest a name. She decided because it had never been done before, requested New Zealand for the name of the asteroid. So that's its official name now. She had discovered it. She wasn't specifically searching for asteroids. She was doing some other work and happened to notice taking images over a few nights. She saw there was something moving and discovered that asteroid. So that's finally, oh yes, the one other thing I didn't mention, this is something that's relatively recent, is that interstellar objects that pass through the solar system, so far 2 have been discovered, and they've got a convention for naming these things. So one being the first, I for interstellar, and then a name, Oumuamua, which is apparently Hawaiian for a visitor who's come from afar, something like that it means. And then Tuai Borisov was discovered by an amateur astronomer. We had a clever scheme to beat the professionals actually to discover this, because the professionals' instruments, they can't really look into the sort of twilightish sky. So he's been still with a fair bit of sky background looking for asteroids in that part of the sky that professional scopes can't look because there's too much sky background. And that's how he managed to pick this one up and beat the sky surveys to finding it. But these are objects that came from deep space, travel through the solar system, were detected, and they'll never return because they're basically travelling too fast. Basically go back into interstellar space. So you never know, you might be lucky enough to discover one of those things, get your name and lights. So that's all. Is there any questions? Hopefully, if you come across these catalogues or wonder why comets are called this or asteroids are called that, give you a bit of an understanding of how it came about. Anything online there at all?